Thanks for your kind introduction. I'm really happy to be here today, unfortunately just remotely. Let me share my screen where I have some slides. Can you see those slides?
Yeah.
Okay, cool. Okay, thanks again for inviting me. Today I'm gonna present a joint work with Andrei Bernstein and Joshua Cobden from NREL as well, and with Professor Emiliano Dallanese from CU Boulder. And yeah, let's go ahead. So power networks, we all know that I've been changing a lot in the last years, mainly because of the advent of, and potentially the network performance could be dramatically improved, because by having generation close to the final use of power, potentially we can have huge voltage drop improvement, we can reduce power losses, and so on and so forth. And also the distribution network can become much more robust and resilient, because it is becoming less dependent from big power plants. However, the fast variability both in load demand and in power generation calls for real-time control and monitoring of such new distribution networks. And thus, state estimation that was once performed mainly on transmission networks, now and always more in the future, is becoming a fundamental tool for system operators. And indeed, millions of sensors have been deployed in distribution network recently. Think, for instance, to smart meters, PMUs, also PVs, to enhance the system awareness. However, these are what we call the heterogeneous sensor with different sampling and reporting rates. Hence, if we want to extract meaningful information from the data that we are receiving, we need to perform the fusion of asynchronous data, which is not always trivial. Moreover, current industrial and utility practices rely on approaches that produce state estimates at the scale of minutes, but potentially measurements from meters, PMUs, and so on and so forth could be processed in real time to produce faster estimates at a faster time scale. Again, to this end, the challenge is that measurements provided by the aforesaid devices are generally not synchronized, and that these sensors do not transmit data to system operator all at the same time. Rather, data are gathered asynchronously. So as a consequence, we might have that a complete snapshot of the entire distribution network may not be available at every time. And hence, traditional state estimation algorithms, which were built on the assumption that instead the number of measurements is bigger than the number of state variables, might not be straightforwardly applied in this new scenario. So what we did is to propose a real-time algorithm that, leveraging a linearized power flow model, updates the state estimates iteratively and by processing measurements as they come in. Okay, let's see a bit of modeling. Now, to have a lighter notation, today I will consider only single-phase networks. However, we treated the more general case of unbalanced three-phase networks in our papers. A single-phase distribution network can be modeled as a graph in which nodes, corresponds to electrical buses, and in which instead edges, correspond to electrical lines. So electrical buses are modeled as follows here. The substation will be labeled as node 0 and modeled as a slack bus, which is basically an ideal voltage generator imposing the nominal voltage of 1 per unit. The other nodes are modeled instead as constant power devices whose power output is basically independent from their voltage. And Pn and Qn here represent the reactive power consumption at bus n, whereas Vn and theta n will represent the voltage magnitude and the voltage angle at bus n. And we collect all the aforementioned quantities in the vectors called P, Q, V, and theta. Regarding lines instead, RL and XL will denote the resistance and the reactance, the else line. And the else line will be, for instance, connecting bus M, bus N. And we have that the grid connectivity is captured by the incidence matrix, whose else row, depicted here, is a vector whose entries are all 0, but a 1 associated to node M, and a -1, which is the source node, and a -1 associated to node N, which is the end node. The grid connectivity can also be described by these matrices R and X here, whose entries are related to the line impedances and to the incidence matrix elements. And these matrices are basically the inverses of the real and imaginary part of the bus admittance matrix, respectively. So let me define here this quantity, V tilde. This is the voltage deviation from the deviation of the voltages from the nominal one that was set to 1 per unit. So it is well known that voltages are usually nonlinear functions of power injections. However, voltage deviations and voltage angle, okay, here, can be expressed as a linear function of the powers by basically taking a first-order Taylor approximation of the power flow equations. And then it will come in handy in a minute to define this matrix phi here. Phi basically allows us to express voltage deviation, voltage angles, and power injections, which will be our measurements, as a function of the power injections. Okay, so as I told you before, distribution networks now are populated by a massive number of sensors. Here in this presentation, for simplicity, I will consider only two kinds of metering devices, namely smart meters and PMUs. So I will assume that if a bus M is endowed with a smart meter, we can measure its active and reactive power demand and its voltage magnitude. So if we stack all these variables in this measurement vector Ym, thanks to the previous linearization, we can express it as a linear function of the power injections, of the overall power injection P and Q, plus some noise introduced by the sensor. Where here, this matrix is a selection matrix that basically picks some rows from the matrix phi introduced before. Similarly, if bus M is endowed instead with a PMU, we assume that it can take measurements of active and reactive power demands, but also voltage magnitude and voltage angles. And then, if this measurement vector can be expressed as a linear function of the power injections, plus some noise introduced by the sensors. And here again, this is another selection matrix that picks rows of phi associated with the mth bus. So now, different from classic approaches, we use the nodal injection rather than the voltages as the state of the grid. This is motivated by the fact that from the former modeling, we have seen that all the measurements can be written as a function, as a linear function of the powers. Moreover, once you are given the power, you can easily compute the voltages by solving the power flow equation. So as said before, we are targeting the case in which we have different sensors with different sampling and reporting rates. So as a consequence, system operators might receive a continuous flow of not synchronized data. And our goal is actually to process this data as they come in to produce state estimates in real time. So our estimator has to produce meaningful estimates even when the number of measurements gathered at each time is smaller than the number of states, or in other words, even if at each time the system is not observable. In the following, the vector yt will collect all the measurements retrieved by the system operator at time t. And again, this can be written as a linear function of the state plus the noise, the measurement noise. Finally, in the following, I will denote the state estimate at time t as x hat of t. Okay, so finally we are at the core of our research. The new estimate is computed by solving this optimization problem here. The first order is a classic least square term. It is convex, but when the number of measurements is smaller than the number of states, it is not strictly convex. The second term instead acts as a regularizer that penalizes the Euclidean distance of the new estimate from the previous one. The regularizer makes this problem strongly convex and hence the state estimate well-defined. And here, this regularizer is weighted by a scalar that we call the inertia parameter that will have a key role in the estimation process, as we will see in a few slides. So since this is a quadratic unconstrained optimization problem, the new estimates can actually be explicitly written in closed form, and it has this closed form here, where the matrix lambda of t, okay, is a symmetric and positive definite matrix. So today I am assuming that the state variation, namely the load demand change, is always bounded by a certain value, delta x, and that also the sensors introduce an error band bounded by a certain scalar value, delta n. However, we consider the more general case in which the measurement error is stochastic in our papers. We are also assuming that there exists a value called tau here, such that every sensor reports its measurements at least once every tau times. So under these assumptions, we prove that the estimation error, denoted here as xi, well, the estimation error is asymptotically bounded by a function of the inertial parameter gamma. So this function here is actually a convex function. We can see here is plot, which means that we can find an optimal gamma that minimizes the error bound. We can actually find it in closed form. It has this closed form here, and we can see that it is basically proportional to the ratio between delta n, the maximum measurement error, over delta x, the maximum state variation. So roughly speaking, we can say that if the measurement noise dominates the state change, then gamma star will be big. And this means that the new estimate will be closer to the previous one, and the measurement noise, it will be kind of filtered out. On the contrary, if the state change dominates the measurement noise, gamma star will be small, because this term here will be big. Okay, so small, big. Gamma star overall will be small, meaning that the new estimate is allowed to vary more from the previous one, to track in a more efficient way the state variation. Okay, now we have some numerical tests. In this case, the tests were done over a three-phase unbalanced test bed, precisely the IEEE 37 bus test feeder. In our setup, we assume that we had 4 buses, the red ones, okay, endowed with PMUs, whereas all the other buses were endowed with regular smart meters. In our numerical setup, state estimation is performed once every minute, and the number of available measurements every time is always smaller than 10, which means that the network at every time is not observable. So in our setup, PMUs report their measurement once every minute, and they introduce a relative error of 0.05%. On the other hand, smart meters are less accurate, and they introduce a relative error of 0.5%. And they report their measurement once every hour. So hence, the constant tau that I introduced before, in this case, which is namely the time needed to gather information at least once from every sensor, is of 1 hour. Okay, so first I analyzed the effect of the inertia parameter on the estimation error. We can see that both a too big gamma and a too small gamma, too big inertia parameter and a too small inertia parameter, see, for instance, the orange and the red curves, do not provide good estimation performance. So as I've mentioned before, when the inertia parameter is too small, the estimate is very sensitive to noise. On the contrary, when the inertia parameter is too big, the estimator tracks slowly the true state. We can see, moreover, that the gamma star, okay, associated with the purple curve, which was computed by minimizing the estimation bound, actually gives performance close to the true optimal one, which are associated with the blue curves. Okay, finally, I compared our dynamic state estimator with the more classic least square estimator, called here LSE. So classic least square estimators, as I was mentioning before, need at every time that the number of measurement is bigger than the number of states. When this is not the case, usually pseudo measurements obtained by using statistical a priori knowledge or of low demands are used. In our simulation at time t, pseudo measurements are chosen as the last measurements retrieved from each sensor before time t. So the least square estimate is then obtained as the solution of this optimization problem here. Again, the first term, okay, is convex but not strictly convex. It is built using measurements retrieved actually at time t, and it is the same that we use to define our algorithm. The second term instead is built using these pseudo measurements and makes the problem strictly convex and then the estimate well defined. So I made a comparison between them. On the left here, we can see the estimation error of the two algorithms. If the inertia parameter is set to gamma star, the value minimizing the error bound, then and it is associated again with the purple curve, we can see that our estimator outperformed the classic least square estimator. On the right here instead, I plot the error in estimating the voltage after solving the power flow equation given the state estimates. And similarly to what we have seen before, we can see that again our estimator can outperform this version of the weighted least square estimator. So finally, to recap, in this talk I've presented you guys a dynamic state estimator tailored for networks of heterogeneous sensors. The state estimator is well suited for distribution network in which at every time the number of measurements is smaller than the number of states because sensors have different reporting rates. Our estimator is shown to outperform the classic least square, that version of the classic least square estimator. And yeah, regarding future developments, we are planning to add constraints, modeling a priori knowledge to the optimization problem used to derive our estimator, and also to use the true nonlinear power flow equations rather than their linearization. Okay, here we have a couple of references if you are interested in knowing more about our work. This concludes my talk. Thanks for your attention. I'll be glad to take any question.
Thank you, Guido. We have time for one question. Yes, Max.
Thank you for your talk. So the functional that you, or the cost function that you're minimizing actually assumes that there is several or a batch of measurements that come at the same time. But I guess the measurements, they all come at different kind of time, right? Or are you bundling the ones that are close enough?
Sorry, do you mean
this one? Yes. Yeah.
This one?
Yeah.
Yeah, no, this one is assuming that we have an arbitrary number of measurements. So YT collects an arbitrary number of measurements, ideally, possibly even one.
Okay.
So this, and as I was saying before, this is convex, but not strictly convex. That's why we needed to add a regularizer. We added another term that penalizes the distance of the new estimate from the previous one. Okay, so in principle here we can have how many measurements we want, because this regularizer allows us to have a strictly convex problem, and then to have this estimate well defined. So this is basically the point of our algorithm. We can have even just one measurement. So super not observable, super lack of information, but thanks to this term, the estimate will be well defined. And moreover, we proved that the estimation error remains bounded. So we are actually able to track the state estimate.
Right,
does that respond to your question?
Yeah, thanks.
Okay, thank you for your question.
Thanks again, Guido. And have a nice day.
Yeah, you too, guys.